Hey, what's up, guys? This is Cheng here. So, LeetCode number 2030, smallest k-length subsequence with occurrences of a letter. So we are given like a string s, an integer k, a letter, and the integer repetition. So a lot of constraints, right? And we need to find the lexicographically smallest subsequence of s of length k that is a letter appear at least repetition times. Right. So the test cases are guaranteed that we have at least a repetition number of these letters in this string, right? So for example, we have the leet, right? And the length is 3, and the letter we're looking for is E, right? So it's E and the repetition is 1, which means we need at least one letter of E. So the answer is EET, right? So for this LEET, since the length equals to 3, right? So we have this one or this one, right? But the EET is smaller than the LEE. That's why the answer is, oh, sorry, my bad. It's not a substring, it's a subsequence. So that's why we have 4 different of at least different candidates, and the EET is the final answer because this one is the smallest, lexicographically smallest, right? And yeah, so in example 2 here, right, similarly, so this time the repetition is 2. We need 2 times of length 4, right? That's why we have the letter. That's why this ECDE is our final answer. Okay. And the constraints are like standard, right? So for this one, so actually this one is very similar to the to a problem 316. So in I think that's a medium problem. So in there it's very similar. The only difference that one is asking to find to find the subsequence. So which that each of the letters appears uh, exactly once. So basically you need to remove some subsequence such that each letter appears exactly once, only one time. So if you guys remember how, because so that one is the same. Similarly for this one, both of them needs to find the lexicographically smallest subsequence, right? One way of solving this problem is not one way. I mean, one of this kind of problems is to use a greedy plus stack. So what does it mean? It means that in the stack we will maintain the letters we have seen so far. Okay, we have letters here. Let's say there's a D here, right? And then the next time we have another letter, let's say if this one is a B, right? Since the key idea here is that we need to find the smallest one. So which means if the second one is B, and if we can pop this D out, right? And then this basically if there's a B, A, D, and B, right? So if we pop this thing out, right, then the AB will be smaller than the AD. So that's the key idea to solve this kind of lexicographic, the smallest subsequence problem, right? Basically, it means that we'll need to use a stack plus some greedy approach. Basically, we're trying to get the smallest subsequence as small as we can by popping by try to pop as many of the bigger letters prior to the current letters, right? Following some constraints, right? And so for the 316, the constraints like if we have enough, if we still have some that the letter we popped left in the remaining strings. If it is, and then if the current one is smaller than that one, then obviously we can pop that out. Otherwise, we cannot pop, right? So that's that constraint. And when we let's come back to this problem. So this one is a hard problem because this one has more constraints. Because not only we have these repetitions, right? So for this one, we only have one letter. We need to worry, and for these letters, we want to make sure this one repeat at least this repetition times. And also we have this k length, which means the length has to be this this length k. Okay, so that's why for this problem we'll be using the similar approach. Let's use this one, LeetCode, as an example, right? So at the beginning, right, we have what? We have L, right? So the L will be pushed here, okay? And then the next one is E, right? So the next one is E. So E is smaller than L, right? And then since the E is smaller than L, and then we were trying to pop this L out, right? But can we pop this one out? Because apparently L is the so in this case we can, because L is not E, right? So we don't need to worry about if we have enough E remaining, right? That's why we can pop this L out. But since we have this K here, right? The length K here, when we pop this L out, we also need to worry. We need to also make sure we have enough letters remaining so that we can get a length K. Because let's say if the K is equal to 2. Uh, no, I think this is not gonna good. This case equals. This is not a good example, but anyway. So when we pop this L out, right? Not only we need to check if we still have enough letters in case this one is this letter, plus if plus with the remaining stack here, right? If we have enough stack here, right? So after popping this out, this is the parts that's left in this one, right? And we also need to check if this part plus the remaining of the string can still give us this k, right? So for example, if this we have this 1, 2, 3, 4, right? So this is a 4. We have 4 letters here, right? And then let's say the k is equal to 7. Okay. So basically, after popping this L out, we have what? We have 4 letters left, right? And then let's say if this one we only have 2 letters left. Let's say this one E, there's like another X here, right? Next, after E. In this case, we cannot pop L, right? Because as you guys can see, after popping L, we only have 2 letters left. Even we concatenate both of the letters with this 4, we still can the longest we can get is 6, right? So that's why oops. So that's one of the conditions we need to check, right? Sorry, let me my bad. So we have L, right? So now we have E, right? In this case, we can pop L. So the L is gone. So now we have E, right? So the next one is also E, right? That's why we can push this E, because E is not smaller than E, right? And then the next one is T. Okay. So T is also greater than E. Okay. Then we cannot pop. And then the next one is C. Right. So the next one is C. Okay. So C is smaller than T. Right. So that's why we can pop this T out. And if we continue, okay, C is also smaller than E. Right. So that's why we can pop this E. But remember, keep in mind that every time we pop like this letter, out, we need to make sure we have enough remaining letters, right, for this repetition, because for this case we can, because we know we have another E after the C, right, and then the repetition is 2. That's why we can pop this E out. In this case, if the repetition is equal to 3, then in this case we cannot pop this E, right? Okay, so we pop this E out, and then the C is also smaller than E, but can we pop this one out? No, right? Because after popping this one, we need 2 E's remaining, but in our case we only have 1. That's why we can only pop this one out, right? So after this one we have a O, right? O is bigger than C. That's why we cannot pop. And then we have D, right? So again, D is smaller than O. Then O is gone. Okay, and we have E, C, D. Okay, the last one is E. Okay, see, so that's why in the end we have this E, C, D, and E for our answer. Okay, yeah, I think that's the main idea, and let's start coding, right? So since we have to check multiple conditions, we'll need several variables to help us. So the first one is the total, right? So apparently we need to know how many counts for this letter in total, right? And then we need a stack. We need the n. We need the total length to compare with the length k, and then we have a stack, right? So this one here. So for I, C enumerate of C. Okay. So first let's try to pop, right? So we pop this stack out. So first we need to know if the stack is empty, it's not empty, and some condition here, right? Okay, so we'll come back to this condition later. Let's finish the other part first. So if a current equals to the thing that we can pop, right? And then what? And then we have a and then somewhere here, right, we're gonna append the current letter here out, right? And then in the end, we do a return of this, right? So that's the basic the basic structure of this solution here, right? But with apparently we need some conditions. So first is that when can we pop? Okay, so the first one is like this, right? So if the stack is not empty and the current one is smaller than the stack of -1, right? So this is the time we want to pop. Okay, and what? So this is one of the conditions, and we need to make sure we have enough remaining strings to make a length k subsequence, right? So that's why we need to do this length of the stack plus the remaining one. The remaining string is n minus I, right? We need to make sure this one is still greater than k, right? That's why this is a second condition. Okay, and the third one is what? The third one is we want to make sure we have enough remaining letters to meet this repetition. Okay. So the third one is that so first if the current one is not if the current I'm sorry, if the letter on the top of the stack is not equal to letter, then we can safely pop it with no issue, or means that this one is equal to the letter, right? If it's equal to the letter, we need to make sure we have enough remaining count to meet the repetition. So we have a count is greater than the repetition, right? Repetition, right? And then we can pop it out. Okay, cool. So, and after that, we pop this one out, right? So it means that, if the current one is equal to the letter, okay, it means that we need to increase the repetition by 1, right? So this repetition means that, how many repetition we still need to build, and this count means that, how many these letters left, right? Since we pop this one letter out from the stack, it means that we need to increase the repetition that we need to build. Okay. And here is and then later on in the end, so if the current one is equals to letter, then we're gonna decrease this remaining count for this letter by 1. So right, this is also obvious. So the next thing is like this. So when can we append this thing, right? So since we have this length k here, we need to add this thing here. If the length of stack is smaller than k, then that's when we can append, right? And once we append that, we also want to check similar thing. If the current one is equal to the letter, that's when we decrease the repetition, right, by 1. So this one is like it's related to this one, right? So when we pop one out, we increase repetition by 1. When we add one of the letter, we decrease it by 1. Okay, so that's the basic one. But this will fail with one scenario. So the scenario is like this. So if we have A, B, 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 C, 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 okay, and the K is equal to 3, and the repetition is equal to 2. So in this case, the correct answer is what? Is A, B, and B, right? But if we follow this code, we just use this code as it is, then the answer will be A, and A, right? Because here, we only pop when the current one is smaller than the top one on the stack. In this case, we have A added to the stack, and then the next one is B, but B is greater than A. So that's why we don't add, right? So that's why the answer is A. So one way to solve this problem is that, when we do the pop here, right, we can add one more condition to do the pop, which is whenever the remaining space in the stack is smaller than the repetitions, then we also pop, right? So which means that, we have A and A here, right? So the next one is also A, but in this case we cannot A because we know the A there's only one space left here, right? That's why we need to also pop it when there's not enough space in the stack for us to fill in all the repetitions. Okay. So I think what we can do is like this, so we have to do something like this. We have to do a parenthesis of this one and then a bigger one here, right? This one is going to be or, right? Or the k minus length of the stack, right, is smaller than the repetition, right? So basically, if this one or there's not enough space for us to place all the repetitions, then we just pop everything. We pop the thing, even though the current B is greater than A, we still need to pop it, right? So I think this should work. Yeah. So if I just run the code, oops. Okay. Yep. Yeah, cool. So this one works, right? I mean, or I think another way of doing this one, if you don't want to mess up with this condition, which is already complicated, I think you can also move this one, this something down here, right? So basically, we add this one. We only add like the letters when there's enough space to add, right? So I think that should also work, which means you need to move this one somewhere below here, right? So even though maybe within this if statement, right? So even though we have enough space, but even though the length of stack is smaller than k, but we also want to check if there's enough space for us left to meet the repetition, right? So that's another way of doing it. Yep, I think that's it, right? So for the time complexity, right, we have a for loop here and we have stack. Even though we have while loop here, but each of the numbers or letters will only be pushed and popped from the stack at most once. So that's why the time complexity is so often, right? And the space is also often, right? Uh, yep, I think that's it, right? So this one, I think the takeaway for this problem is that next time when you guys see this kind of get the lexicographically smallest subsequence of a string here, try to use a stack, right? Try to use a stack and to greatly try to improve the subsequence by removing the top one, while following some of the constraints depending on the problem, right? And the rest is just like implementation details. Cool. I think I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.